Hi, I'm Andy Pernsteiner, Global Field CTO for VAST Data, and today I would like to talk with you about the first application for the VAST Data platform. We call it the VAST DataStore. It's actually something that we've been providing to customers for the past 4 years. So at VAST Data, as we embarked on our journey to build a next-generation data platform, we had to decide where to start. And at its foundational layer, we wanted to start where the data lived, that is to say, the state layer. Now, if you think about AI, machine learning, and deep learning, the foundational principle is that they revolve around data. They are driven by data. And so we needed to build something that would be flexible and scalable to allow for the applications of tomorrow to be able to run today. So where do we start? Well, initially, before we started writing a single line of code, we had to identify some principles to guide us on how we were going to build this platform. And to start with, we wanted to simplify everything. And what does that mean? Well, what it really means is that customers want to be able to deploy, manage, maintain, and scale systems without having to worry about complexities. As our R&D team went through the iterations of building the platform's initial stages, they really focused on making sure that at every decision point, there was no complexity or burden added, which would translate to any customer dissatisfaction. And so our real goal was to make it very simple because we knew that would make it much easier for people to deploy at scale. The second thing that we needed to make sure is that it was open in terms of being able to be accessed by many different types of applications, whether it be file server applications, object API applications, whether it be machine learning applications that hadn't been generated or developed yet. We wanted to make sure that all of the standard APIs and protocols were available on the platform without having to go and shoehorn things together. When we focused on this area, we really wanted to make sure that everything that we added to the product was complementary and would extend the ability for more applications and workflows to use the system as time went on. And then finally, we wanted to make sure to give customers ownership, not only in terms of how they deploy it in their data center, but also in terms of how they might deploy it in the cloud or at the edge. This gave them the flexibility to choose the way that they would scale both the capacity and the performance of a platform without having to worry about necessarily where it was deployed or what types of hardware that they would use. In fact, we wanted to make sure that we focused solely on allowing for a platform that could be deployed on ubiquitous hardware that could be mixed and matched as a customer saw fit. As you might imagine, over time, hardware, cost, and the cloud providers will offer different types of underlying infrastructure, and so we wanted to ensure that that could be something to be leveraged by the platform as we went forward. The last thing that I wanted to underscore was the fact that these three principles really tie back to the same principle, which is the first principle, which is to simplify everything. If we give people the ability to deploy on any platform, if we give people the ability to deploy with any application using any interface that's going to be supported down the road, it just means it's easier for them to do, it's simpler for them to use. They don't have to worry about having tons of different ways of doing things. It wasn't enough for us to focus on building a next-generation data platform. We also needed to make sure that we had a platform that could scale and be performant in the age of AI. Now, if you consider the way that AI and machine learning work, they need a lot of data to train on, and they need to do it at scale. This requires a persistence layer that is not only very flexible in terms of its ability to scale to be large, but also the ability to scale to be fast. Not only that, the era of AI brings to us workloads which could be batch-oriented, could be real-time, could be operational and transactional in nature, and we needed to make sure that whatever platform we built would be able to handle all of those in concert at the same time. Before we started building, we also researched the products that were available on the market today to be able to solve this problem. And no matter how hard we tried, we couldn't find something that would solve it in a single unified way. There were point solutions which were very good at transactional and high performance workloads. There were performance solutions that were very scalable but had issues with resilience and manageability. There were different APIs and protocols customers were wanting to use, and in many cases, they would have to deploy separate point solutions for each. Deploying the solutions and having different ones for each different type of data or different type of workload is one thing, but imagine having to manage moving data between those different silos and making sure that your applications and developers knew how to access data on different platforms. It wasn't really a good recipe for success, and we found that because of all of the trade-offs that customers had encountered in the past, they were continuing down this path of building a tiered architecture. At the heart of the reason for many of these different tiers of storage were a series of trade-offs. You could either have something that was fast, but not inexpensive. You could have something that was scalable, but difficult to use. And when we looked at all of these different options, it just made sense that if we could break those trade-offs, we could find a new way forward. The other thing that we found is that customers would end up having different sets of storage, not necessarily based on the speed that they wanted, but maybe based on the way they wanted to access the data. What this led to was copying of data. Now, copying is one thing, but another challenge that customers had was the ability to track what they'd copied and where it was. This led to bad data lineage and data governance and left application developers in a place where they were unsure if the data they were accessing was the actual source of truth or whether it was something that was derived based on something else. This led to a lot of complexity in the data center, and customers honestly spend a lot of their time and energy making sure to wrangle data into a way they can manage. Now, in order to be able to manage all of this and handle all of this, you need a place to put it that's very scalable and can continue to keep up with all of the different ways that people are processing data. AI and machine learning really bring to bear the fact that there is a fundamental challenge in data storage and data processing that gets worse and worse the more data that you need to process. So we needed to solve for that. As I mentioned earlier, customers are typically building silos and making copies of data, and ensuring that all of that is managed is a challenge. But when you think about AI and deep learning, you really want to train on the whole corpus of data. You don't want to just train on bits and pieces at a time because you don't get the full insight out of what you're trying to gather. And so in order to make sure that you actually get accurate answers out of your data, you need to have it all in one place. And you need to have it in one place that can allow you to scale both capacity and performance as your needs evolve. As we looked at all of the challenges facing people today and what the impact of those challenges and trade-offs were, we realized we had to do something better. And so what we did is we created the first universal data store that is an all-flash architecture, which allows customers to consolidate multiple tiers of storage into a single data store platform. It is the first act in our great journey to allow customers to process all of their data, and not only process data that they're working with today, but also to unlock value from data that they will process in the future. VAST created a new architecture that we call DAYS. If you want to know more about the VAST DAYS architecture, we have another video in this series made by our co-founder, Jeff Denworth, which goes into much more detail. I will give you the high level, which is effectively that we've taken the state layer and the logic layer and we've separated them from each other. We've allowed for anything within the logic layer to perform compute functions against anything within the data layer. And so we've allowed for scalable processing and scalable capacity without the trade-offs of the past. At its core, VAST created something new called the element store. The element store is a highly flexible, highly scalable, highly efficient way of us to store data on hardware. The way that we handle it is effectively we take different types of hardware, whatever happens to be the most cost-effective, performant, or next-generation technology available at the time, and we allow for it to be addressed in a byte-addressable manner. We take metadata and we intelligently lay it out on the lowest latency flash available, and we take data and we lay it on the lowest cost flash available. This combination of metadata and data is forming what we call the element store. Now, what's an element store? Well, an element store is a place where we can store any type of elements. An element can be a file, an object, a table, a block device. We actually don't even know what the next thing is that we're going to put on it, but we hope that you will. At some point in time, you have to find a way to store data in a way that allows for not only highly resilient storage of data, but you also have to do so in a way that's performant and scalable. The element store is built with scale in mind, in fact, with exabyte scale in mind. Most platforms out there were built in an era where petabytes was the largest anything would ever go. We started in the world of petabytes, and we are now seeing customers deploying in hundreds of petabytes and even starting to talk to us about the exabyte scale platforms they want to build. It's not enough to store things in a manner that's highly efficient. You need to give access to it. And so what we've done is we've created a series of interfaces into the element store to give customers full access to their data, regardless of what their upstream applications are. For example, side by side within our platform, we support protocols such as NFS, S3, and SMB, alongside the ability to store files and tables on the same element store. When I say tables, I mean things like SQL tables, the ability to have SQL dialect talking directly to the same platform that you have object APIs and you have file protocols talking to. This is something that we've created, and we've done so in a way that layers everything side by side. There's no stacking of our protocols. There's no stacking of our interfaces. Everything has native access directly into the element store, which you might think of as a highly scalable key value store, but it's so much more. Speaking of resiliency and durability, I want to make sure to underscore the fact that anytime data is written into the element store, it lives somewhere stable. There is no such thing as a cache on our system. There is no such thing as an unstable write. We actually don't even have that concept within our code. Not only is it much more effective at being able to store customer data, it's also much easier for us to write software for because we don't have to worry about things like cache coherency. We don't have to worry about things like unstable writes. Up until now, I've been talking a lot about AI, but we also have to remember that the dawn of AI also means that enterprises of all shapes and sizes are going to need to take advantage of it in order to keep their businesses running. We didn't want to just make a platform that was good for AI or HPC or machine learning. We wanted to have something that all enterprises could deploy. And in order to do this, we needed to have all of the features that they were used to having on all of their existing platforms. We needed to expose those features in a way that gave them the control they needed, the flexibility they needed, and the data protection that they needed in order to continue adding more and more data to the platform. Because if you keep in mind that AI and machine learning allow enterprises to take full advantage of all of their data, it's not enough to just store a subset of data on this platform. You need to store it all. And that even includes data that may not have been historically viewed as being analytical data. Today, they're not just servicing single applications or single departments. They span multiple departments, multiple applications, businesses, use cases. When we build for modern enterprises, we have to behave like we're building for a service provider. We needed to make sure that we implemented features that enabled zero trust security to be deployed. Features like all of the encryption standards that we've ratified, external key management, all of the security features that we built are in support of our ability to support the private and public cloud providers of today, as well as enterprises who are embarking on their own journey of building hybrid clouds. It's not enough to be able to build a platform that is secure and can store all of customers' data. It also has to be cost-effective enough for them to do it at scale, and not only for a small amount of their data, but for all of it. To do this, we had to spend a fair amount of engineering effort researching the best ways to store data at scale on all flash architectures. And we came up with a series of technologies to be able to do this, and they act in concert to be able to provide this to customers in the most cost-efficient way possible. The first of which is we effectively said, let's use the lowest cost flash that's available on the market today, and the lowest cost flash that will be available in the future. Now, when we did this, we had to create a lot of software to make sure that every time data was written, it treated the flash as gently as possible. This not only enables customers to use the lowest cost flash, but it also allows us to offer up to 10-year guarantees on anything that's deployed because we believe that much in our ability to be able to sustain the longevity of low-cost flash. If you compare that with what other platforms have historically done, that's more than triple the lifespan that most vendors are willing to stand behind. In addition to allowing customers to use the lowest cost flash media, we had to make sure that it was as efficiently used as possible. The existing erasure coding and RAID schemes that were on the market and were in the scientific communities were not sufficient for doing this at scale, and so we had to create our own. We've actually gotten to the point where now we can deploy flash in such a way that you can get 97% utilization on flash. It's unheard of. Typical systems top out at around 80%, and we are significantly higher than that. That results in less flash that needs to be deployed for a customer and less cost. Not only are we able to use the lowest cost flash and do so in a very efficient manner, we are also able to come up with new ways of storing that data on flash with new data reduction techniques. In fact, we had to invent new ones, which really drive down the cost of what customers have to deploy. In fact, it's very unheard of in the unstructured data world to get additional data reduction, but VAST has a way to do so. Why did we do all of this? Well, of course, we want to make it less less costly for customers to deploy. But if you really think about it, our goal is to allow customers to store everything on us. And in order to do that, we need them to eliminate cost from their decision matrix. Now, many of you who have been in the data storage world before have understood that there are concepts such as compression and deduplication, and there are pros and cons to each of these approaches. Compression, for example, is great at squeezing the most out of all of the data that you store, but it's typically very constrained to a small subset of data. For example, you can only compress a small amount of data against each other because it's inefficient to do at scale. Deduplication, while more scalable on one hand, is much coarser grained, and so you will miss opportunities for data reduction because it's not fine-grained enough. So when we looked at all of these techniques that were available, we realized we had to do something better. And so VAST created something called similarity data reduction. Similarity gives you the best of both worlds, where it can compress as though it were local, but it can do so at a global scale. The VAST DataStore, in essence, looks like one big zip archive, with the exception that we don't have to decompress unnecessarily and we don't have to waste a lot of cycles compressing. Now, it's not enough for us to invent a new data reduction algorithm. We also wanted to take the existing ones that were out on the market today, such as compression and deduplication, and combine them with VAST similarity data reduction to give customers a much better ability to store data efficiently. In fact, what we found is that across our entire customer fleet, we're at about 4-to-1 data reduction. Maybe that doesn't sound like a lot to some people, but if you think about things at a petabyte and then exabyte scale, that's a significant amount of reduction in spend and a significant amount of reduction in the power, cooling, and footprint that are required to deploy anything at scale. Okay, so we talked about how VAST is much more cost effective, but really what does that mean from a customer standpoint where they already have an existing platform? If you think about all flash platforms today, they're typically quite expensive, and so VAST has definitely been able to come in and be significantly more cost efficient than those. But what about tiered or hybrid architectures? Well, if we go back to our original thesis, we felt that customers were not able to unlock value out of their data because they had it in a tiered architecture. So our goal is really to replace the tiered architecture. We don't want to be cheaper than the most expensive thing out there. We want to be more cost effective than even the blended cost of a system that was designed to be less expensive. And so VAST, in many cases, is significantly cheaper, not only than all flash-based platforms, but also than those who are comprised of many tiers of storage. Now, what does it mean for you to be able to put everything into a single platform that isn't in a tiered architecture? It means that access to data is immediate. It means that responsiveness is guaranteed. It means that anytime data is requested by a user or line of business or application, there's no need to copy it from some other platform in order to be able to stage it first. It's already there, and that's how you can really unlock insights, by having data on a single platform that's always able to provide fast access. So what's another advantage to having all of your data on a platform that allows for instant real-time access to data? Consider that when HPC, AI, and other jobs are scheduled, the CPUs and GPUs can spend a fair amount of their time just waiting for data. That's known as I/O wait time. And if you reduce the I/O wait time down significantly by having low latency access to data, you actually get better utilization out of all of your CPUs and GPUs. This can result in a significant job runtime savings, but can also result in the ability for customers to deploy less compute and GPUs, which not only allows them to reduce the cost of their storage, but also of their compute. It's not enough for us to make something that's cost effective and has the features that are needed for enterprise data protection, data scalability. It's also important to handle the performance aspect of it. Now, if we think about the historical ways that customers were storing and processing data, they kind of had two choices. They could go with a network-attached approach, but there were bottlenecks in the network-attached storage protocols to be able to unlock insight from that data. So there are inherent bottlenecks in many of the protocols, which really limit the ability for applications to process data. The other option customers had was they could go and deploy a parallel file system. The challenge on that end of things is that typically parallel file systems can be quite bespoke, require special clients, and a lot of care and feeding. What we really needed was to offer customers the performance of a parallel file system with the ease of use and simplicity of a network-attached storage platform. So this is where we came in and decided, let's go and look at the available storage protocols today and extend them in a way that allows them to be used for more high-performance applications. Some examples here would be the implementation of NConnect, RDMA, and GPU Direct Storage. Speaking of GPU Direct Storage, it allows for applications that are using GPUs to not have to wait for data to pass from main memory into GPU memory. Speaking of GPU Direct Storage, it allows for applications to process data without having to wait for the transition of data from main memory into GPU memory. This elimination of an extra step does a few things. First of all, it reduces job runtime, which ultimately accelerates time to insights. The second thing that it does is it actually reduces the amount of work that the GPUs have to do in order to move data from one place to another. Put another way, we actually allow for GPUs to be used more for science and less for data movement. It would be one thing if customers could deploy this solution and use one of these different options to access their data, but of course at VAST we want them to have all of them available. And not only that, they could have all of them available all of the time. So for customers who had not yet deployed GPUs in their environment, they need not take advantage of GPU Direct Storage today to get best-in-class performance. But as their needs evolve and as their applications and as their environment evolves, VAST allows them to use those new technologies and techniques without having to move data or move to a new platform. So when we built this data store, in order to satisfy the needs of the data platform, we need to make sure that we could not only scale capacity, but also performance. And we wanted to do so in a way that allowed customers a lot of flexibility, but we had to solve the scale problem. Because when we looked at other architectures, we found that as they continued to scale, they started having issues with things like lock management and cache management. East-west traffic is a big problem on scale-out architectures, and it requires that a lot of care and feeding go into making sure that things are running smoothly. In fact, many of the customers that we talked to when designing our products said that most of the scale-out architectures that they deployed were ones where they had to limit the scale of each of their implementations because they were too fearful that they would have issues. A common issue that happens in a traditional scale-out architecture is that a single failure can cascade into impact across the entire platform. That's not okay for people who are running large numbers of jobs in a multi-tenant environment. So when we built something, we wanted to make sure that we could not only allow for fast access to all of your data, but also do so in a way that allowed for each of our independent, stateless compute nodes to be able to access all of the media and all of the global namespace in parallel. What it means is that when there's a component failure in our platform, it doesn't impact anything else that's going on. There's no east-west traffic, there's no lock management, there's no cache management. None of these things that people have had to worry about in the past are things that they have to worry about now. So effectively what we've built is a system that's faster than a parallel file system. In fact, it's more parallel than a parallel file system. When we looked across what customers were using our system for, we actually started noticing that there were workloads that they couldn't run on parallel file systems that they were running on VAST. Maybe couldn't, it's a strong word. The reality is they could run it on something else, but it would be significantly slower. Take, for example, AlphaFold, which is effectively a Google application that handles a complex problem known as protein folding. The issue that customers would have if they were running this on a parallel file system is that it requires large number of GPUs to be able to memory map significantly different portions of the file system at the same time. This wreaks havoc on parallel file systems because they have to route everything through metadata controllers, and they can easily become bottlenecked and bog everything down. VAST doesn't have to worry about any of these things because everything that we do is embarrassingly parallel and doesn't require any bottlenecking on any independent servers. Everything that happens in a sharded fashion. So for applications like AlphaFold, we can speed up these workloads by a factor of 5 to 1. This makes us appear much more like local NVMe from a latency and performance standpoint, but remember, it's in a package that allows for scalability to petabytes and exabytes and allow for accessibility from many, many different systems at the same time. So you get the benefits of fast NVMe storage, but you get the flexibility and scalability of a network-attached platform, all without requiring a parallel file system driver. Now, I've talked a lot about HPC and AI and parallel file systems and parallel problems, but there's another edge to the parallel side of things, which is you might have enterprise applications, for example, database workloads, where you want to make sure that they can not only deploy at small scale, but also at large scale. Imagine you had hundreds or maybe even thousands of separate databases running on a platform at once. you need to make sure they can all perform well. What we found is that historically, people would not use network-attached storage platforms for database workloads because the I/O profile is extremely small and random. At small scale, it wasn't that big of a problem, but as you continue to add more and more database servers, you would find not only that would you have a ceiling for performance, but you'd also hit a cliff where things would degrade. On VAST, not only can we continue scaling, but even if we hit a performance ceiling based on the hardware that customers have deployed, there is no degradation as more threads or concurrency is added. And so customers can feel comfortable not only deploying HPC and AI applications, but also more traditional transactional applications on the platform without having to worry about any contention or any degradation in performance. If we think about all of these things put together, what we've built is a platform that can not only house data, which is required for AI, machine learning, and deep learning, not only can it house transactional data for database workloads, not only can it house unstructured data for file and object workloads, but it can kind of do them all. So in short, because we can provide the ability for customers to run such a wide and diverse variety of applications on the platform due to our ability to support the performance requirements and the scale requirements that customer applications have, it really makes it so that customers can deploy everything in their data center with a single unified data store. Now, it would be one thing if we had done this and only a small number of customers had deployed it for a small number of niche applications. But the reality is that in just 4 short years, we have hundreds of customers deploying us for a large variety of applications, and they are trusting us with the most important asset they have, which is their data. In fact, to date, we now have 10 exabytes worth of data under management. And these are assets that customers rely on day in, day out for not only operational analytics, but also for next generation insights. It helps them keep their lights on, and it gives them the ability to continue to grow and scale their applications as their businesses evolve. Another thing I'm excited to introduce you to is not only the platform that we've built, not only the data store layer that we've built, but if you think about it, when data is stored on a platform, not only do you want to be able to access it and be able to process it as fast as your applications can handle, but you also want to know the data that you have. You want to understand more about the data that you have. And for that, we leveraged another piece of technology that we built known as the VAST database. There's another video on that, so I won't go into those details, but what I will say is that the first practical application of the VAST database is the VAST data catalog. Effectively, it allows us to index all metadata attributes related to any piece of data that lands on the platform in such a way that customers can gain insights about the data that they have. It unlocks new ways for them to be able to analyze data because no longer do they have to maintain a separate place for storing metadata about their platforms. Think of it another way. If you have data that comes into a system and you need to know about it, how do you know how to find that data? In the past, people would deploy separate point solutions to index and update metadata, where on our platform, all of that happens automatically. It's fully integrated and there is no additional configuration to do. You just get a catalog out of the box. Effectively, we store every single metadata attribute, and this can range from basic things like timestamp information to permissions and ownership, file name and path, but it can also extend into things like user-defined metadata. Imagine you had a platform where if you updated a metadata attribute on one of your data objects, that we'd automatically catalog that, and you'd be able to do analytics against those tags or against that metadata without having to maintain a separate system and without having to go and do any expensive file system tree walks. So what that really unlocks is the ability to start thinking about your file system like it were a database, or maybe to think about your database like it were a file system. For example, what happens when you have a series of images that are uploaded into your platform where you want to perform inference and annotation? You want to understand what is being stored on your system, and so typically what people have done in the past is they would create directory structures or file naming techniques. For example, they'd have a directory called ingest, and they'd have another directory called processed. And whenever they would run some kind of job, they'd need to copy data from the ingest directory over to the process directory. Now, this is error prone and also results in amplification not only of the amount of data storage required, but also in the amount of processing and I/O required. But what if there was a different way to do it? What if instead you could store metadata attributes on any individual file or object and then allow your applications to query a catalog so that they would know what was processed and what wasn't? without having to do some rudimentary walk through a file system tree. Effectively, we allow people to store their data in the way that it's generated, not try and shoehorn it into directory structures which are antiquated. What we've done is effectively brought the ability to search at scale any attribute on your file or object platform to be able to use for further analysis. Another thing that maybe I didn't mention was the fact that you can store many types of attributes on your files or objects. In fact, you're not limited to one key value pair. You can have many. And imagine the scenario where if you're trying to search for something on a traditional platform, you would have to come up with some complex command and series of statements to find it. Whereas with VAST, you can effectively just use a simple SQL query and you can find everything you want in a way that's very intuitive and comes back very quickly. This enables the next generation of applications to be able to do their processing because they don't have to spend time looking for data. This enables data engineers and data scientists the ability to keep iterating more quickly because they don't have to worry about how things were organized. So to review really quickly, we provided standard interfaces to access all file and object data. But what I didn't mention earlier is that we're allowing customers to do this at scale in the cloud, at the edge, in a data center. It doesn't really matter to us where it goes. And we have another presentation related to the data space, which I hope that you'll enjoy. Effectively, just keep in your mind that we have this platform. It exposes many interfaces which allow customers to use any application that they need. It's very fast. The system is very resilient. But now imagine this at a global scale. Imagine you could deploy this anywhere, on-prem or in the cloud. So to recap, today I've walked you through the VAST DataStore, a universal place to put all of your data, regardless of the application, the I/O profile, the scale of application, the concurrency. We've allowed for customers to deploy everything in one place and know that it is not only resilient and fault tolerant, but also can perform to the highest levels that their applications demand. Thank you for allowing me to walk you through an overview of the VAST DataStore, a foundational element of the VAST Data Platform. To learn more about the VAST Data Platform and the other ways that we're leveraging it, please check out our other videos in this series. Thank you very much.